The engineer's analysis may take place early, say after the first exploration well is drilled and evaluated, or later, perhaps after primary recovery is complete and improved recovery processes must be considered. Ultimately, the analysis may be repeated and modified many times during the reservoir's life as additional data is collected. To make these estimates, we incorporate the equations of fluid flow, as well as a description of the reservoir and fluid properties, into a mathematical model which represents reservoir behavior. Ideally, the behavior of the model matches that of the actual reservoir and can be used to test and compare development strategies before they are implemented. This reservoir model is then coupled with an economic model, which takes into account prices, capital investments, taxes, and so forth. The two are used to compare alternative strategies from a technical and economic perspective. The reservoir model can be a physical model, as in the case of sandpack studies of waterflood sweep efficiency, but more likely it will be a mathematical model. In numerical simulation, the reservoir is divided into a grid or cell system. The system used to represent the reservoir may be a two-dimensional aerial model, as we see here, or a two-dimensional cross-sectional model, or a more elaborate three-dimensional configuration. Values of porosity, permeability, fluid saturation, and pressure are assigned to each grid block. It is at this point that the engineer and geologist need to work together closely to be sure that a proper description of each block in the reservoir is being made. Once this is done, the appropriate system of equations representing fluid flow in the reservoir are solved at finite time steps, so that a time-lapse picture or map of pressure and saturation changes can be determined for each grid block as fluids are produced from some wells and injected into others. We simulate, then, producing conditions that could take place in the reservoir. If we do not like the outcome, we try another strategy until we find the one that is optimal. This allows us to make our design mistakes in the office quickly at low cost, rather than in the field at high cost.